Good afternoon. Welcome to Tuesday, everyone. Oh my goodness, it is almost noon. We're getting started a little late. Well, we had a chance to discuss parabolas in life. So we were taking a look at this ball flight here, and what we discovered was we could create a function, or well, an equation that would describe this ball's flight. Our x values here, what do our x values represent, class? Here's another question. How far away from the hoop is the player? About 6.5. Yeah. So x values represent what? X. It's a unit of measuring how far away the hoop is horizontally. What are my y values? Alexander. Yeah, well, 2.5 would be the highest point of this ball here, or maybe even close to 3, because that's 3 up there. So it's like nearly 3. 3 what? I don't know. 3 units. Okay, this y value measures how high the ball is, and the x value measures how far the ball is away. So and when we put a parabola through the center of mass of the ball, we found that the trajectory of the ball is modeled very precisely by that parabola. And we predict, it's still hard to predict whether this ball is going to go in or not, but we see it's at least not an air ball. It's at least going to hit the rim, or it might go rim and in. Might go rim and out. We're not sure. It's not going to hit backboard, though. So, and what kind of parabola is that? Well, the sliders tell me that it's y equals negative 0.2 x squared plus, what was that one? 1.5? 1.5x, there it is, plus 0. So we don't need to add the plus 0 because c is 0 because, hey, it's a y-intercept is 0, and that's what the information that c gives us. So that's where this parabola goes. And today we're going to look at a note that's going to teach us more about the different anatomy of these parabolas. More complex than lines. Parabolas have a lot more going on than a line. So we need new vocabulary to discuss the key features of the parabola. So let's take a look at our note, and we'll go through, we'll fill it out together. The graph of a quadratic relation is called a parabola. And so that's why when Isaiah said we should actually play basketball in math class to practice our parabolas and practice our quadratic relations, I said, but we don't have 2 basketballs. We need a pair of balls to look at parabolas. Okay, so that's not the best one. All right, so anyway, that's what we have a parabola. A parabola is an arch-like shape, and so we see these arch-like shapes here. We're going to be discussing these various parabolas A, B, C, and D, and they can either open up or open down. The following 4 graphs are all parabolas. So A opens up. So just make a note on there. Opens up. B opens down. All right, so just make some notes on there and get your handwriting all over this to demonstrate your learning. And there's many important points to these parabolas. And some of these important points have the following names. The vertex is one important point. The axis of symmetry is another point. The axis of symmetry, what's the axis of symmetry of your face? Oh, Fisher's showing me, but he showed it by karate chopping his own face. Yeah, your nose. Yeah, your nose is the axis of symmetry of your face. Some of us might not have very symmetrical faces. Sometimes that can be very attractive. Generally, we think of symmetry as very attractive. And then there's zeros, the zeros of parabolas. And so strap in tight, everyone, for a wild vocabulary math ride. First, we're talking about the vertex. It's a fancy word, starts with V, ends with X. So if you're a Scrabble player, it's a great word to have in your vocabulary. What? Vertex. Because X is an 8-point tile, and V is a 4-point tile. Those are all high point tiles, and they're particularly hard to use, hard to combine V and X in the same word. So anyway, the what? The what? The vertex. Practice spelling it once. The vertex is the point at which the parabola reaches its maximum or minimum height. The following letters are often used to represent the coordinates of the vertex, H and K. So here, I want you to be in the habit of like, what does that mean? I don't know. Let me draw a parabola. I guess this is the point here, HK. HK. Okay, so let's go back to my picture of a parabola, my perfect basketball parabola here. Where is the vertex of this parabola? At about what? You do like hot and cold. Tell me when I'm getting there. Hot, 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 hot. Okay, thank you. Yeah, it should be a little more enthusiastic. But they're at about 3.75, 2.813. Okay, that's the vertex. And we would call that points H and K. H would be 3.75 and K would be 2.8. All right? We're going to use those letters H and K later on. So you kind of want to have them in the back of your mind. But the main thing is to see that's the maximum value of the parabola. That's the highest it ever gets. Hi. And yeah, so that's a key, like a very key point of parabolas. Isaiah called it the turning point at the beginning of class, and that's a great way to think about it. Where does the parabola turn around and go the other direction? In this case, it's a maximum value. If the parabola opens upwards, it's a minimum value for the parabola. All right, let's keep going. Okay, so the y coordinate of the vertex K is called the maximum or minimum. It's called the maximum or minimum, or the maximum or minimum value. So you could even add the maximum or minimum value here. Yeah. For each of the four graphs shown, determine the coordinates of the vertex, the optimum value, and state whether the parabola has a maximum or minimum height. Oh yeah, that's also right. We can also call this the optimum value. I never say that. You know how you could say, like, you could call it, like, you know, a dance move might have 5 different names and you only use one of the names? Yeah, I'm like that. So we can call this also an optimum value or a maximum or minimum value. I always say maximum or minimum. I never say optimum value. So let's take a look at our parabolas on the other side and locate the vertexes. Where is the vertex for A? Someone tell me the point at which A has its optimum value. In this case, it's a minimum value. Ashley. 0, 1 is perfect. So you label it, put it on there, put a dot, label the point 0, 1, and then flip over the page, and you're going to say graph A, the vertex is 0, 1. The optimum value, it's 1. Okay. So why is the optimum value 1? Well, that's the value of y at the vertex. Hello, Alex. Yes. Could you imagine if I said no? No, don't go take care of your medical needs. All right, so here, optimum value. The height, what kind of thing is it? Does it have a maximum or minimum? Is this a maximum value for the parabola or a minimum value for the parabola? That's a minimum. It never gets smaller than that. It gets down really close to there, and then it turns around and says, now I'll go the other direction. Okay? It doesn't actually have a personality and desires, but I like to think of it as such. So this is a minimum value. Let's take a look at graph B. Where's the vertex for graph B? Draw a picture. 0, 4. Yes, 0 in the X, 4 in the Y. Very good. So there, we're going to transfer that over here. It's 0, 4. The optimum value is therefore 4. And the height is A. Is that a maximum or minimum? Maximum. That was a max. Imum. Because that parabola opened downwards. So it has a maximum height, and then it gets lower on both sides. C. Quicker now. Where's the vertex for C? Draw a little point on there. Label it. Negative 2, 1. I like how you went alphabetical there. Negative 2 in the X and 1 in the Y. That's my common mistake, is that I will often say 1, negative 2. Although since I've been describing that as a mistake I often make, I don't make that mistake anymore. It's like a self-unfulfilling prophecy. The optimum value here is just the Y value. So is it negative 2 or 1?
1.
1. Good. Is it a maximum or minimum?
Maximum.
Yeah, that parabola also opens downwards. It's also the maximum value that parabola reaches, then it turns around and goes the other way. Now let's take a look at D. Where is the vertex for D?
1 minus 3.
1, negative 3. 1 minus 3, also good. 1 dash 3 would be a little confusing. 1, negative 3, what's the optimum value? It's the y value, minus 3, and it was a minimum. Because it opened upwards, right? Yeah, it opens upwards. Okay, yes. Opens upwards. So there's our 4 parabolas and their vertexes. Now, the vertex is a super important point on the parabola. We're often very interested in the vertex. If you remember the lemonade example we looked at yesterday, where the maximum profit they could make was based on the price per glass, there was a point where they made 0 profit because their profit per glass was 0. And then as they increased the price per glass, their profit went up until it went down again when no one was buying it anymore. So the point in between was the vertex. That was the highest point. That was the optimum profit they could make. So that's why we call it an optimum value. It often optimizes what you're looking for. Okay. So next is the axis of symmetry. Fisher described the axis of symmetry as of his face by doing this. It is the line upon which your face is symmetrical, right? So it's oftentimes your nose. Your nose is like an axis, okay? An axis, another place we see axis in math is the y-axis and the x-axis. Okay, these are lines. Axes are lines. And parabolas are symmetrical with respect to a vertical line through its vertex. This line is called the axis of symmetry. Axis of symmetry. You guys know I'm an English teacher too, right? So why am I capitalizing these words? I should not have capitalized those words. They can be lowercase. Anyway, for a parabola, the axis of symmetry is always parallel to the y-axis, and it passes through the vertex. So what does that mean? For each of the 4 graphs shown, we want to determine the equation of the axis of symmetry. All right, so I'm going to start drawing on my parabolas some axes of symmetry. So go back over there, and what you're going to do is you're going to look here and you're going to say, what line is this parabola symmetrical around? Symmetrical around the y-axis, this one. This one's symmetrical around the y-axis. So what's the equation of the y-axis? Y equals whatever the heck it wants, and what does x equal? 0. The equation of the axis of the y-axis is x equals 0. Okay, this is the line for which x equals 0 and y is all the possible values. So I could draw this on, but it's not going to show up, right? So boop, there's the axis of symmetry. So there, the axis of symmetry there is the y-axis is x equals 0. So if I look at our other parabola that we had over here, we're going to go back to this one. Here, is this parabola symmetrical around the y-axis? No. If I reflect this in the y-axis, I get something different entirely. But its axis of symmetry is over here, the line x is equal to 3.75. So let's put that on, actually. Let's graph that line. X equals 3.75. Notice that is a line. It goes directly through the vertex. And it is the line around which the ball goes up, hits its optimum value, or we wouldn't talk about this as the optimum value of a basketball. We would say that's the maximum height of the basketball. And then it falls down again in a symmetrical line going up and then coming back down. And then here is where it reaches the same height as the release point. And it's symmetrical around this axis of symmetry. You can see it. The ball goes up, and what comes up must go down. Symmetrical. Okay, let's keep going. So now we have x equals 0 for that one. If you recall, B also has its vertex on the y-axis. So its axis of symmetry is also x equals what? Also x equals 0. Remember, that's an equation, and it describes all the points for which x equals 0. Y could be anything. There's no limitations on y. Y goes up to negative infinity and positive infinity there. Okay, but now let's take a look at C and D. Let's get them both at the same time. That way you have some time to do your own questions. This video doesn't have to be 80 minutes or something crazy. So, where's the axis of symmetry for C? What negative 2? How would you describe that with an equation? Yeah, x equals negative 2. So here's the line x equals negative 2, and I'm just going to put it on there with a little dashy line. And that's the axis of symmetry. we'll sometimes abbreviate that to the AOS, x equals -2. Okay, the axis of symmetry. All right. Now, how about this one, D? Where's the axis of symmetry for D? It's a line around which the parabola is symmetrical. What's the line? Oh, x is equal to 1. Yeah. So the line x equals 1 here is the axis of symmetry. AOS x equals 1. The axis of symmetry is x equals 1. So put those on your note here so you can remember for the future. X equaled -2 for C, and x equals 1 for D. All right, let's carry on. So now let's take a look at zeros and what zeros are. Okay, so zeros have a number of different definitions for zeros, and I'm going to give them to you here. We don't actually have space inside the note, but it was a PDF and I couldn't modify it, but we can modify it with the miracle technology of our pens. So zeros, or these are also called roots, and that'd be the word that I use the most frequently, or x-intercepts, or solutions. So many different words for the same thing. Okay, right, so just get those different words in there. Maybe put boxes around them all. Zeros, roots, the x-intercepts of a parabola, or solutions to a parabola. Okay, the zeros are where the parabola crosses the x-axis. Oh, okay, cool. These points are also known as the roots, x-intercepts, or solutions. Since the parabola is symmetrical, the axis of symmetry is exactly halfway between the two zeros. This is going to be very useful. If you can find the places where the parabola equals 0, then you can find the optimum just by taking the average of those 2 points and then calculating for x. So a parabola doesn't always cross the x-axis. That's a really important notion. It's not like a line, where if a line exists and it goes off to infinity, it will always touch both the y and the x-axis once, unless it's parallel with one of them, in which case it will always touch once. But parabolas, no, because parabolas have minds of their own. They turn around and go the other direction. So first, let's gather our zeros from A, B, C, and D. So let's go over here. Where are let's start with B. Where are the zeros for B? Read. -2 and 2. Circle them and label these points. This is the point 2, 0, and this is the point -2, 0. Okay, label the zeros. All right, and then come on over here and fill it in for B. Oh, was I showing? Yeah, I was. Okay, good. There's my zeros for, yeah, that's good, Reed. Those where they are. And here we go. So B has zeros at 2, 0 and -2, 0. If I told you that a parabola has zeros at 2, 0 and -2, 0, where would you tell me the axis of symmetry was? As x equals 0. Yeah, because the axis of symmetry will be right in between the two zeros. So if one's at -2 and the other one's at 2, and it's right in the middle. It's right on the y-axis. And indeed, that's what we have here, where we have our axis of symmetry is the y-axis, and therefore the two zeros are on opposite sides. Where's the zeros for A?
Black, right?
Thank you, Boston. That's so kind. Yeah. So where are the zeros for A? There aren't any zeros. There are no solutions to that parabola. There are no zeros. See, right? There's 0. There's none of them. There are no zeros. Okay. So, yeah. So we want to be able to recognize these situations. A, none. Nada. You could also write nada. None, nada, zilch. Okay? You write the word that you think is the most fun. All right. Now let's take a look at C. So where are the zeros for C? Can you see the zeros? That's right. The zeros are at -3 and -1. Circle those points, label them. You do it on your own, and then I'll do it. Here we go. -1, 0, and -3, 0. Okay. All right. So there we go. So that's where they are. -1, 0, and -3, 0. So if that was all the information you had, you can now say, well, -3, -1. -1 plus -3 is -4. -4 divided by 2 is -2. So I expect to find the vertex where x equals -2. Dun, 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 dun. There it is. -2. Right in between, right? It's the average between those two things because it's symmetrical. Okay, how about the zeros here for D? 0, 0, chicken 0. And this one, 2, 0. Winner, winner, chicken dinner. Okay. So there. And there, again, the average of 2 and 0 is 1. That's where we find the axis of symmetry. La-dee-da. Okay. So now let's keep going. Now I want you to draw a situation where a parabola has 2 zeros and a parabola has 1 0 and no zeros. Okay. So what does this look like? Well, we've seen some examples of 2 zeros. So it's not hard. Just draw a picture, right? So here's 2 zeros. Here is no zeros. Could be opening downwards as well and be below. Okay. Has a vertex that's below the x-axis. Never touches. What about the situation where it has 1 and only 1 0? How would we do that? Alexander?
Maybe make it so the very top it reaches, but that would be it.
So it's. Would you say that it's optimum value? Is that the?
Yes.
What were you gonna say, Isaiah? Just like. Yeah. Like the parabola comes down, touches the desk, and comes back up.
Yeah.
Can you do it like the parabola for the basketball, like that, where it only goes through the.
Yeah, but there I was starting at a point. If you take a look at the basketball again, the basketball has 2 zeros there and there. But what would happen if I shifted the axes up there? Like if I did this, where if I click on the picture here, I can actually change the picture so that the basketball does that. Right? And then all I need to do to now optimize this is I just need to change that C value. Let's readjust our C value here. About there, right? About there. There. Okay. And now move the whole picture up. See there. Now this has a single root, right? That's right here. It's about there. It's not perfect, but it's very, very close. If the vertex is the one and only root, that's the only way to have one root only. Okay. So there, a case where we have 1 0, you can draw 2. Draw one opening up, so it might look like this, and boop, touch, and turn around. And another one, woo, boop, just kisses the x-axis and goes the other way. Okay. There's 2 different cases of 1 0. Johnny.
Could you also do it where like the thing just goes up and it gets like to the 0 0, like on the.
Sure.
Okay.
Yeah.
That's what I did.
Let's do one in Desmos. This is the most important one to understand for today, and it's y equals x squared. Look at that. How many zeros does that have? Just one. And it happens at 0 0. And here, let's connect a table of values. If I input 0 for x, what's y? What's 0 squared? You can take the square of 0. Yeah, it's just 0. Yeah, so that's fine. I could also have negative x squared. Boop. And that also has 1 0 at 0 0. So does negative 6x squared, or negative 1 over 6x squared. Has also a single 0, and that happens at 0, 0. If b and c are both 0, so ax squared plus bx plus c, when b and c are both 0, its vertex is 0, 0. And that's the family of quadratics for that. Let's keep going. All right. Okay. Put your mask on, Mr. Jennings. Teach class. All right. So now you have some examples that we can do together, and that you can also continue on your own. All right. So let's do some of these together. Here is graph the data in the table of values and answer questions about the parabola. First, let's analyze this data here. Okay. So we're going to first do first differences and second differences. And this was a review from yesterday. So for first differences, I started at 12 and I went down to 5. What happened to that number? What's flavor of 7?
Negative.
It got 7 smaller. And then it went from 5 to 0. What did that do? Negative 5. Went from 0 to negative 3? From negative 3 to negative 4? From negative 4 to negative 3? It was negative 4 yesterday, and today is negative 3. Is it colder or warmer today? Warmer. 1. Yeah, so it became 1. From negative 3 to 0 is 3, and then 5, and then 12. Sorry, and then 7, Mr. Jennings. Is that a line? If I graph these points, do they all happen on a line? How do you know they're not a line? Yeah, because it's a problem, Mr. Jennings. You know it's not a line because the first differences are...
It's a parabola.
Yes.
But the answer would be 2 for the second difference.
Yes.
They each go down.
Yes. Yes. So it is not a line because first differences are not constant. Because the second differences are constant, the negative 7 to negative 5 is an increase of 2. Negative 3 to negative 5 is an increase of 2. 2. I go from 1 to 3, that's an increase of 2. I go from 3 to 5, that's an increase of 2. 5 to 7, increase of 2. This is all the same. Therefore, it's a parabola. It's quadratic. So it's quadratic because the second differences are all constant. So now we can graph our points on here. And so we just read off our points. X is negative 2, Y is 12. So go ahead and find that. Here is negative 2, and then you go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and put your point on. Okay? And we also found some zeros here. Here's a 0 at X is 0, and X is 4. So I'm going to go ahead and graph that 0 right now. I'm really excited to graph that 0. And I'm really excited to graph this 0 here at 4. Okay? So these are some things I noticed. Here's a key point. That's 0, 4, 0. And here's another key point, 0, 0. Those are both zeros or solutions. If this has a 0 at 0, 0 and a 0 at 4, 0, where's the optimum value? Where's the vertex? Here's my 0 and my other 0. Or my solution and my solution. Or my root and my root. Yeah, 2, negative 4 is the vertex. So let's put that one on. 2, negative 4. All right? And then there's also these points that we can graph 1, negative 3. So go as 1, negative 3. Okay, so I put on 2, negative 4 in the wrong way. This is 2, negative 4 down here. Okay, this, I don't know what I was thinking. I wasn't thinking. I apologize so much for this point here. This is a mistake. Okay, and so now I have the bottom of the parabola. I can start graphing it in here. And then I know that this one will be, this one up 3, so it's going to go up 5 for the next one. Notice if it went up by 1 here, and then it went up by 3. The next one is going to go up by 5, and then it's going to go up by 7. Okay, so I go up by 5 here. This is going to be the point 5, 5. So there's 5, and there's 5. So 5, 1, 2, 3, 4, 5. There it is. And I can also graph the symmetrical point on the other side. It's over there. And then this point is going to be symmetrical over here. It's right there. Okay. Why is it symmetrical? Because it's symmetrical around this axis of symmetry. And the equation of the axis of symmetry is x equals 2 is the axis of symmetry. And then just bring your curve through these other points and make it beautiful. Take pride in your parabolas that you draw. Make them pretty. or handsome. Your parabolas can look however they want to look. All right. And so then another thing to do is add arrows to your parabolas. What's the significance of those arrows on the ends?
Showing the direction it's going.
Yeah, that's right, Jeff. It shows that it keeps going to infinity in both directions, in the x and in the y. All right. So now, there, what are the coordinates of the vertex? Well, we can label that. And it asks us to label that. So the coordinates are 2, -4. What is the optimum value? It's -4. Okay, so I would just answer these down here. What's the equation of the axis of symmetry? What's the equation of the axis of symmetry? What is the equation of the axis of symmetry? X equals 2. Good. Yeah. What are the zeros of this relation? Yeah. The origin, 0, 0, and 0. No, not 0, 4. 4, 0. I was about to say yes, absolutely. That's very true. Because it doesn't mean anything to me, one or the other, until I realize I'm talking to someone and it has to make sense to them too. So it's 4, 0. X is first. Okay. Notice the sign of the second differences and the direction of opening. Okay, so this is what I want you to notice. Notice that the second differences here are all positive. What that's telling you is it's changing how quickly it's sloping in a positive way. It starts with a very strong negative slope and then achieves a slope of 0 right at the vertex. And then its slope starts growing on the other side. So its slope is constantly growing, and its slope grows at a constant rate. Maybe you can see it better with the ruler. If I have a ruler there that I bring down, its slope changes at a constant rate around the parabola, starting from very negative to flat to very positive. Okay, all right. And so we don't want that. Okay, so now you can graph this one too. Okay, so this is one that you can do on your own. I want you to do your first differences and your second differences, plot all your points, and then answer these questions. And then let's take a look at the back. The zeros of a parabola are x is equal to 0 and x is equal to 3. The second differences are positive. Okay, so if I give you information like that, would a sketch help you understand that information? How would you draw a sketch with that information? The zeros of a parabola are x is 0 and x is 3. How would you sketch that? How would you start your sketch? Well, I would do this. I would draw an x-axis and I would draw a y-axis. And I know that the zeros are x is 0 and x is 3. Okay, so there's going to be zeros there and there. The things I don't know is I don't know if it does this or this yet. But I told you that the second differences are positive. Over here, we had an example with second differences that are positive. Notice that the slope is always getting more and more and more slopey in a positive way. That creates a parabola that opens in what direction? Actually, it has this vertex down. We say this opens upwards. It's like if it does this, if it's a bowl collecting rain, then it's open towards the top. An umbrella that shields you from rain, a parabola that goes like this, is opening downwards. So an umbrella opens downwards, a bowl opens upwards. So when the second differences are positive, they open upwards. When the second differences are negative, they're going to open downwards. So this one, if the second differences are positive, it opens in what direction? This opens upwards. So where will the vertex be relative to these two zeros? Sorry? Yeah, below. And will it be closer to one of the vertexes? Sorry, one of the zeros? No. It'll be right in between those. It could be here. That could be the vertex. And then you've got a sketch that you can use to answer these types of questions. Now, you want to be able to draw these sketches, but you want to start being able to visualize these in your mind. So when you see a parabola, visualize it. If I tell you it opens upwards, C, the parabola in your mind opening upwards. If I tell you it opens downwards, C, an umbrella. Okay. So is the y value a maximum or a minimum value in this case? It's going to be a minimum. And is the y value a positive number or a negative number? Is the optimum value of this parabola the y value of the vertex? Is the optimum value a negative or a positive? It's going to be a negative because we're down here in negative territory. And then it says the points. Oh, this is a new parabola. Okay, determine the x value of the vertex. That's still part of the same. So what's the x value of this vertex here? I'll label them. 0, 0 is one root, and 3, 0 is the other root. So the vertex, we usually call that h and k. K could be any negative number. Where were we? Oh, yes, we want to know the x value of the vertex. If they're here 0, 0, and 3, 0, where would the x value be? Yeah, 1.5. Yeah, half of 3 plus 0 is 1.5. The average of 3 and 0 is 1.5. So, yeah, h is equal to 1.5. And if you're saying h is equal to 1.5, that's really good because you remember that we usually use h and k as the coordinates of the vertex. So that's cool. And then here, if 3, 2 and 9, 2 are on opposite sides of the same parabola, let's see if you can tell me the equation of the axis of symmetry. I'm going to do one more thing before I stop the video and let you guys work on your own. Sorry, let you people work on your own. I'm going to show you the family of parabolas that all have zeros at 0, 0 and 3, 0. So it would be parabolas that look like this. Some stretch factor A multiplied by x minus 3. Okay, I'm going to add my slider A, and there. See if I zoom in, and you'll see there. See, it has vertex. It has zeros at 0, 0 and 3, 0. And then this is a parabola that opens upwards. I can also create parabolas that open downwards, but they would have second differences that are negative. So that would tell you that it opens downwards. And then, here, let's take a look at the vertex. There it is, 1.5, 1.35. So I'm just going to put that line of the axis of symmetry, x is equal to 1.5 here. And notice that as I look at the infinity of parabolas that have zeros at 0, 0 and 3, 0, okay, that I'm getting always a vertex that is on that axis of symmetry. Doesn't matter how stretchy I make it or whether it's positive or negative, the vertex is always there. Okay? And I can even do this. This is fun. Whee! And then you just sit and watch the show. Maybe we get Connor's musical note to give us some musical accompaniment to this beautiful mathematical dance. So that's the anatomy of a parabola. There's one other thing that that I kind of want to talk about, and that's the y-intercept. The y-intercept of these parabolas is another interesting point that we might want to talk about. So let's take a look at our first few parabolas and just highlight the y-intercepts. Over here, with A and B, it's less interesting. The y-intercept is also the vertex. But with C, what's the y-intercept of C? Sorry? The y-intercept of C is negative 3. It's the point 0 in the x and negative 3 in the y. That's the y-intercept. And here the y-intercept is also 0, 0. Okay? So that's the y-intercept. It's one of the zeros. Okay? So here it's useful to notice the y-intercept of different parabolas. And I'll teach you how to manipulate those things in the next lesson. Bye for now, everyone.